Next up, we're going to do an example where we actually do have to think about converting our coordinate system in a meaningful way. So we're going to try to evaluate the surface integral f dot n ds over the hemisphere. Oh, that's a bad M. Hemisphere z equal root 9 minus x squared minus y squared with disk x squared plus y squared equal, less than or equal 9. Sorry, your book is telling me that that disk is spelled with a K. In the xy plane, oriented outwards for f, and I want to have to convert this afterwards, so it's going to be 1/3 x cubed, 1/3 y cubed, 1/3 z cubed. Okay, so that's the problem we're trying to solve, and I'm going to sketch it real quick. So here's x, y, and z. Here's the hemisphere. Now let's try a little better. Okay. So this top part is the hemisphere, z equal root 9 minus x squared minus y squared. And then this bottom part right here is going to be x squared plus y squared less than or equal to 9. These are hitting at radius 3. And it's oriented outwards. So the problem is to evaluate a surface integral across this surface that's really made up of two separate parts, this hemisphere on top and this disk on bottom. But since we are thinking about those two different parts, this is a closed surface. And then f is not weird in any way, it's continuous. So since this is a closed surface and I'm finding a surface integral, I think divergence theorem is going to help me out here. And that's decide. Decide to do divergence theorem, since this is a closed surface. And so we're going to need to compute the divergence. So we'll go ahead and do that here. Divergence is d dx of the first component cubed plus d dy of the second component plus d dz of the third component. And this is just going to become x squared plus y squared plus z squared. So that's the thing that's going to go inside our surface integral. And then the region is just a hemisphere. With radius 3. So we're going to think about, since it's a hemisphere, I think spherical coordinates are going to help me out here. So my theta spins all the way around. I've got like a full circle disk in the xy plane, so I know that theta should go from 0 to 2 pi. My phi starts up here, and then it ends down here. So I know that my phi goes from 0 up to pi over 2. And then since I've got radius 3 everywhere on my hemisphere, I know that my rho should go up to 3. I'm going to erase that arrow and then write my rho again. Okay, so I have the ingredients of the divergence theorem so far. I started with a surface integral, it was oriented outwards. And then I can convert it to a triple integral over my region of del dot f dv. And I found the bounds for my region. I found my del dot f, so I could go ahead and start plugging stuff in. I said that my region goes from 0 to 2, 0 to pi over 2, 0 to 2 pi for bounds d rho, d phi, d theta. My rho went from 0 to 2, my phi went from 0 to pi over 2, and my theta went from 0 to 2 pi. And then I know that I need my rho squared sine phi every time I have that dv term in spherical coordinates. And then my del dot f I found before was this x squared plus y squared plus z squared. And so this is going to be one of those problems where we have to go ahead and convert after we've computed the divergence to the coordinate system we want to use. So it's fine that I took the divergence in Cartesian coordinates, x, y, z. Once it's in this integral, it doesn't really matter where it came from. I just know that this is a spherical coordinate problem, and so the integrand, the thing inside the integral, needs to be in spherical coordinates. So x squared plus y squared plus z squared we know is just rho squared. So that's going to be 0 to 2 pi, 0 to pi over 2, 0 to 2, rho to the fourth, sine phi, d rho, d phi, d theta. How are we doing on time? Yeah, I can evaluate this. Okay. So it's been a while. We may as well work through it. Integrating rho to the fourth is going to become 1/5 rho to the fifth, evaluated from 0 to 2. That's what this part was. Sine phi is a constant as far as rho is concerned, so it can just stay out. And so that's going to give us 0 to 2 pi, 0 to pi over 2, 1/5, 2 to the fifth minus 0. So we can pull our constant out front. Go 0 to 2 pi, 0 to pi over 2, integrating sine phi d phi. And so when we look at this part, we just have to integrate sine phi, which when you take derivative of sine, it becomes minus cos. Yeah. So I'm pretty sure I get the negative sign here. Oh no. So that becomes integral from 0 to 2 pi of minus cosine pi over 2 minus cosine 0 d theta. So I know cosine 0 is 1, so this is going to become 1. Minus becomes plus 1. 1 minus cosine pi over 2. I think that's the one that has roots in it, so I'm not going to do it. But it's a constant, so it can come out front. And we're evaluating 0 to 2 pi of d theta. So that's just going to become theta evaluated from 0 to 2 pi. Which is just 2 pi. If I had a calculator, I would plug that in and get the answer. But we're just going to leave it like this. And so that tells us the flux through the top of the sphere as well as the disk at the bottom. So if you remember doing a similar problem for just like the open component of the top of a sphere, and you're confused about why this answer isn't the same, the reason is because this is actually looking at the flux through two separate surfaces.